Hello, welcome to Basics of Finite Element Analysis Part 2. In last module or last lecture, we had discussed weak formulation, and what we are going to do today as well as in the next class is develop weak formulation based finite element equations for an actual problem. And in this problem, we have a bar which is being exerted, which is being subjected to external forces. Some of these forces are tensile in nature and others are tractional in nature, and we will try to develop solutions for this problem using the finite element method. And in finite element method, we will use the weak formulation to develop the solution. So, first let us look at the bar problem. So, you can have a bar and its cross sectional area is Ax. Actually, it is not cross sectional area, it is so Ax is Young's modulus, and that could also vary with respect to x, times cross sectional area, which is this thing. Okay. And this problem, I could apply some external force F, and I could also apply some traction force like this. So, the governing equation for this kind of a problem in general can be written as d over dx Ax du over dx. So, the displacement at any point is u. So, u is a function of x plus Cu equals q, and let us say the bar. So, let us say the length of the bar is L. So, here the domain is x is equal to 0 to L. So, this is the length of the bar. This is my coordinate origin. So, x is equal to 0 at this location and x is equal to 0 at x is equal to L at the other extreme end. Now, if I have to develop a formulation for this problem, the first step finite element formulation is, so the first step is that, so this is my domain, so the first step is discretize the domain. So, I break this up So, in this case, for purposes of simplicity, I will break this entire domain into 3 elements. So, this is element number 1, element 2, element 3, and we will just assume for purposes of simplicity that each element is of equal length. So, we have 3 elements, each L by 3 long. Okay. The next step is that we assume a function for ux for each element. We assume a function for ux for each element and then develop a weighted residual function, and develop weighted residual statement for each element. For each element u, for each element u is varying over the length of the element. So, this is nothing but some interpolation functions times uj for each element. Okay. So, uj's are constants and they are unknowns, and psi j's are known assumed functions. And there are n such functions. So, I am going to add this up over n terms. And also we assume a weight function. So, weight function, because to develop this weighted residual statement we have to assume u and we also have to assume weight function. So, weight function is Wi is equal to psi I x and I is equal to 1 to n. So, we will take different weight functions in this thing. So, with these things now we develop. So, we have developed a weighted residual statement. We can plug all this. So, let us call this equation A, let us call these equations B. So, we plug B into A to get weighted residual statement. But we have seen that if we have a regular weighted residual statement, the differentiability requirement for psi j is higher, and it has to be, at least in this case, it has to be at least quadratic. So, we will weaken the differentiability requirement by going for the weak formulation. So, we will say now develop weak form of weighted residual statement. So, this is an additional step because now we are using a weak formulation. So, the weak form of the weighted so first we will write the strong form, then we will write the weak form. Okay. So, my domain of integration is he plus 1 minus d by dx a u prime plus c u. I mean, in reality I have to replace this u by this entire expression, but for purposes of brevity I am not doing that. And now I am multiplying it by weight function psi I dx is equal to he plus 1 q psi I dx. This is the strong form. This is the strong form. And now I will mathematically manipulate the strong form to convert it into a weak form by integrating by parts. So, what I get is he plus 1 d psi I over dx a du over dx plus c u psi I dx is equal to q psi I dx integrated over the domain of the element, and plus I get some extra boundary terms. So, I get psi I evaluated at x a q a, and I will define these entities later, plus psi I x b evaluate times q b. So, these are the two extra terms. These are the terms, boundary terms. When I do integration by parts, I get those boundary terms. We had seen that. So, these are these things. And here q a equals minus a u prime evaluated at x a, right. So, what is x a? This is actually, to be consistent, what I will do is I will erase these limits and I will call it x a, x b, x a, x b, x a, x b, x a, x b. Okay. So, this is eth element. Its first coordinate is x a and second coordinate is x b. So, q a is minus a times u prime evaluated at x is equal to x a, q b is equal to plus a u prime evaluated at x b. So, this one is the weak form. And here the differentiability requirement on the weight function and the primary variable is same, right. So, that is why and it is lesser compared to the strong form. So, this is the weak form, and we know that u, what is u? We had assumed that u is this function, right. U is this function and the weight function is this psi I. So, once again in the weak form I can take different values, I is equal to 1 to n. So, this represents n equations, it represents n equations. So, now what we will do is we will replace u by uj psi j x, and because it is for the eth element I have these superscripts e. So, we do this and what we get is x a to x b, and now because I am having, we are talking about eth element. So, I am going to just psi I superscript e times a times d over dx uj psi j plus c psi I, and actually this has to be summed up uj psi j integrated with respect to x equals q psi I dx x a to x b plus I get this boundary term plus I get the other boundary term. So, I will just call this boundary term as B1 and I will call it B2. Okay. And now Uj's are unknowns, but they are constants. Psi j's are known functions. Psi j's are known functions. So, I will reorganize this thing. Once again, these are n equations and I will reorganize this thing. So, what I will do is I will bring this summation sign outside the integral. So, I integrate it from x a to x b t psi I e over dx a d psi j over dx e plus c psi I psi j So, this is the expression which I get. Just note that uj is now outside the integral sign, and the reason I could take it out is because it is a constant. So, when I differentiate it, it becomes 0. So, the only thing which matters when I am differentiating this term, I am sorry, this term, this entire thing is psi j. I can take out uj outside because it is constant, right. So, this is the, so again this represents n equations for eth element, and how many variables are there? N variables. It has having n variables, not variables, n unknowns, and these are uj's. So, for the eth element there are n unknowns which are uj's, and we have n equations. So, now I can express this in a matrix form for the eth element. I can call this entire thing is Ke, it is being multiplied by a vector Ue, which is Uj, and this is equal to Fe. So, this gives me force F plus I get another vector Q E from B1 and B2. From B1 and B2 I get QE. So, here Kij for the eth element is T psi I over dx A d psi I over dx, excuse me, j So, this is the definition of K matrix. The definition of Fi is Q times psi I times dx, and my Q matrix it will be essentially minus AU prime evaluated at XA and AU prime evaluated XB from B1 and B2. So, this is QA and this is QB. oh I am sorry, this has to be multiplied by psi I times x a, psi I times evaluated at x a times psi I evaluated x b. So, this is the element level equations, and they are n element level equations, and they involve n unknowns which are u's. And now what we will do is we will actually compute these values. So, we will actually compute actual values of these K matrix and F matrix and Q matrix, and for this we have to actually know the definition of size. If we know the definition of size, then we can differentiate it and integrate it and we can get the values. Now, in part 1 we had discussed that for a two noded element for a bar we can have linear approximation functions, right, and we had developed the relations for those functions. So, we will use the same linear approximation functions in this case, but before we do that, what we will do is, see here the integration is happening from x a to x b, and this is the global coordinate system. So, here x is equal to 0, here x is equal to L, and for instance in this case x a will be L by 3 and x b, for second element x a will be L by 3 and x b will be 2 L by 3. But what we will do is we will go to a local coordinate system because it makes our computations faster. So, before we actually calculate, we will develop local coordinate systems. So, suppose you have an element and its global coordinates are x a and x b. So, this is coordinate x. Then, so this is global coordinate system. Then what I do is I develop another coordinate system and I call it x bar, and this is local coordinate. So, this local coordinate system means that it is valid only for eth element. This is eth element, it is only valid for eth element. Beyond eth element it does not matter, it does not, it is purposeless. So, in this local coordinate system, at x a the value of x bar is 0 and at x b the value of x bar is h e. Okay. So, these are the local coordinates and these are global coordinates, and h e is equal to x b minus x a. Okay. Now, given this, we see that dx is same as dx bar. Okay. So, with this transformation we will calculate the values for elements of K matrix, F matrix and stuff like this. So, for local coordinate system, my interpolation functions are psi 1 x bar. Now, psi 1 is a function of x bar, not x, and this is equal to 1 minus x bar over h e, and psi 2 which is a function of x bar is equal to x bar over h e. Then d psi 1 x bar over dx is equal to minus 1 by h e, and d psi 2 over dx bar is equal to 1 by h e. So, let us calculate K11 for the eth element, and I will use local coordinate system to calculate it. So, my limits will be, when it is x a it becomes 0, and when it is x b, x bar is h e, and here in this relation I replace I with 1 and j with 1 to calculate K11. So, d psi 1 over dx is minus 1 by h e, and I assume that a is constant, and d psi j is what? 1. So, it is 1 by h e plus c times psi 1 x, because psi is psi I psi j, right. So, this is 1 minus x bar over h e, and psi j is 1. So, it is again 1 by x bar over h e dx. So, what I get is a over h e plus c h e over 3. And if I do the math, similarly K12 for the eth element, if I do the same thing, 0 to h e minus 1 by h e a, oh, there should be a negative sign here, I am sorry, there should be a negative sign here, because j is 1. So, for while calculating K12, it is 1 over h e times a times 1 over h e plus c times 1 minus x bar over h e times x bar over h e dx, and this we get as minus a by h e plus c h e over 6, and we find that K21 E is same as K12 E and K11 E is same as K22 E. If we do the calculation, this is what we find out. Likewise, we can also calculate the force vector. So, F1 E, what is force? Force vector is q times psi I dx. So, F1 is q times 1 minus x bar over h e dx integrated between 0 to h e, and that comes to be q h e over 2, and F2 E is equal to q h e over 2. So, ultimately I get a element level equation as this 1 minus 1 minus 1 1 a over h e plus c h e over 6 2 1 1 2, and this entire thing is added up and multiplied by u1 e u2 e, and this equals q h e over 2 1 1 plus q1 e and q2 e. So, this is the element level equation, and in this element level equation again we have two unknowns. These are the two unknowns, right. C, A, Q, all these parameters are known. So, we have two unknowns and two equations, two unknowns and two unknown constants and two equations. Okay. So, in the next class what we will do is, which is the last class of this week, is we will now assemble these equations and also apply boundary conditions. So, then that will give us a comprehensive overview of whatever we did in the last course. So, thanks a lot and look forward to seeing you in the next class.